Hey, what's up everyone? In this video, I'm going to show you how to prove big omega. So for example, prove that 8n to the power of 3 plus 5n squared plus 7 is big omega of n to the power of 3. The idea is very simple. So here is our red function. So this is this one, and this is our green function. And we just want to show that our red function grows faster than our green function, or the red function is always above the green function starting from n0 and onwards. So I hope that makes sense, and let me just say it one more time just to be clear. All we have to do is find a coefficient c and a positive number n0 such that from this point and onwards the red function is always above the green function. And that is how we prove big omega. So we have 8n to the power of 3 plus 5n squared plus 7. And we'll start off with this being equal to itself. And you'll see why I do this in a second. So 8n to the power of 3 plus 5n squared plus 7. Now the next step is I'm actually going to erase the equal sign and also erase this number 7. So what is our operator going to be here? Is it going to be greater than or less than? Well, obviously, this here will be greater or equal to this, right? Because we just remove a plus 7. Now, I'm going to do one more step, which is remove the 5n squared. And this right here is still greater or equal to 8n to the power of 3. This means that we already found our constant c. So there we go. We found our constant c, and the next step is to find the positive integer n0. So let's try n equal to 1 and see if this inequality is true. So we have n equals to 1, so 8 times 1 to the power of 3 is 8 plus 5 plus 7. Is this greater than or equal to 8? And the answer is yes. So over here, you're going to have 20, and 20 is greater than or equal to 8. And now we write the conclusion. So by definition, 8n to the power of 3 plus 5n squared plus 7 is big omega of n to the power of 3, because this right here is greater than or equal to 8 times n to the power of 3 for all n is greater than or equal to 1. So this here is our constant c, and this is our n0. And that's it. That's how you prove big omega. It is time to look at the formal definition of big omega. So f of n is big omega of g of n if we can find a positive constant c and a positive integer n0 such that f of n is greater than or equal to c times g of n for all n is greater than or equal to n0. Prove that 8n to the power of 3 plus 5n squared plus 7 is big omega of n times the square root of n. Our proof will be very similar to the previous problem. We're just going to write out 8n to the power of 3 plus 5n squared plus 7. And we know that this is greater than or equal to 8n to the power of 3, right? Now, since 8n to the power of 3 is greater than or equal to 8n squared, and 8n squared is greater than or equal to 8n to the power of 1.5. And remember that if you have n times the square root of n, this is the same as saying n times n to the power of 1 over 2, which is n to the power of 2 over 2 times n to the power of 1 over 2, which is the same as n to the power of 2 over 2 plus 1 over 2, which is n to the power of 3 over 2, and this is the same as n to the power of 1.5. So this here is equal to 8 times n and the square root of n. Let's rewrite our inequality. So we have 8n to the power of 3 plus 5n squared plus 7, and this is greater than or equal to 8 times n and the square root of n. We found our constant c. Now let's find n0. So we're going to substitute n is equal to 1 and see what happens. So we have 8 times 1 to the power of 3, that's 8, plus 5 plus 7. Is this greater than or equal to 8 times 1 times the square root of 1, which will also give us 8? Well, the answer is yes. We have 20 is greater than or equal to 8. So by definition, 8n to the power of 3 plus 5n squared plus 7 is big omega of n and the square root of n. Since this is greater than or equal to 8 times n square root of n for all n is greater than or equal to 1. So here we have our constant c and our integer n naught. Prove that 2n to the power of 3 minus 7n plus 1 is big omega of n to the power of 3. So why don't you pause this video and try on this problem, and then we'll go through the solution together. Are you ready? Okay, so we'll start with 2n to the power of 3 minus 7n plus 1, and I'll say that this is equal to itself first. Now, if I remove the plus 1 over here, of course this will no longer be an equal sign, but what will it be? Will it be greater than or equal to, or less than or equal to? Well, you guessed it, over here is greater than or equal to this expression over here. So what are we going to do next? Well, I'm going to show you a technique that I want you to know. Instead of writing 2n to the power of 3 minus 7n, we will write n to the power of 3 plus n to the power of 3 minus 7n. And it means the exact same thing. And I'm also going to put parentheses around the last part. Since n to the power of 3 plus n to the power of 3 minus 7n. Now actually I'm going to write an equal sign and write the exact same thing on the right side. So notice that this here is a polynomial to the third degree. It's n to the power of 3. And if you subtract n to the power of 3 with a linear function 7n, you're not subtracting much, right? You're really not subtracting much. So when you subtract, this will still be positive. This will be a positive function. Now with that in mind, if I remove this part over here, then what sign will we have? Is it greater than or equal to, or less than or equal to? Well, of course it's going to be greater than or equal to. So since n to the power of 3 plus this part is greater than or equal to n to the power of 3, we can rewrite our inequality up over here. So we have 2n to the power of 3 minus 7n plus 1, which is greater than or equal to n to the power of 3. And this is the same as having a coefficient 1 times n to the power of 3. This part makes sense because it's like saying a is greater than b, and b is greater than or equal to c, so a is greater than or equal to c. So you can see that's the case here. This function is greater than or equal to this, and then we write it down here, and we found that this is greater than or equal to n to the power of 3. So it makes sense that our original function is greater than or equal to n to the power of 3. We found our c. Let's find our n naught. So let's try substituting n is equal to 1 and see what happens. So we have 2 times 1 to the power of 3 minus 7 times 1 plus 1 greater than or equal to 1 times 1 to the power of 3, and see if this inequality is true. So here we have 2 minus 7 plus 1 is greater than or equal to 1. So we have negative 5 plus 1 is negative 4. Is this true? Well, the answer is no, right? So n naught cannot be equal to 1. We try again with n equal to 2. So we have 2 times 2 to the power of 3 minus 7 times 2 plus 1. We have 1 times 2 to the power of 3. So here we have 16 minus 14 plus 1. Over here we have 8. So this is 3 is greater than or equal to 8. Not true either. So we have to increase this to a 3 and see what happens. 2 times 3 to the power of 3 minus 7 times 3 plus 1. 1 times 3 to the power of 3. This will be 54 minus 21 plus 1. This is 27. We have 33 plus 1 gives us 34. And so this inequality here is true, and therefore n naught will be equal to 3. And the last step is to write the conclusion. So by definition, 2n to the power of 3 minus 7n plus 1 is big omega of n to the power of 3, since our function is greater than or equal to 1 times n to the power of 3 for all n is greater than or equal to 3. Prove that 3n log n minus 2n is big omega of n log n. So we're going to write out 3n log n minus 2n is equal to itself first, and then we're going to keep on simplifying. So what's going to happen if I make this n log n? This will no longer be an equal sign, but what will it be? Is it greater than or equal to, or less than or equal to? It's greater than or equal to. The easy way to understand this is, let's say if I use a different example, if I have 3x minus 2 is equal to 3x minus 2. Now I make this x, right? So you end up subtracting more on the right hand side. You end up subtracting more. So that's why this will be greater than or equal to. So I hope that makes sense. Now 3n log n minus 2n log n is just n log n. And we can write this as 1 times n log n. So we found our c. Let's find our n naught. We're going to try with n naught. So we have 3 times 1 log of 1 minus 2 times 1. Is this greater than or equal to 1 times 1 log of 1? Well, log of 1 is 0, right? Log of 1 is 0. So we have 1 times 0, which is 0. Over here, it's the same. So we have 3 times 0, which is 0. And we have 0 minus 2. So we have negative 2. Is this greater than or equal to 0? Well, the answer is no. So we increase this to a 2 and try again. 3 times 2 log of 2 minus 2 times 2. Is this greater than or equal to 1 times 2 log of 2? Well, in computer science, when we say log, right, we actually mean log base 2. That's just how it is in computer science. Log base 2 of 2 is 1, and 1 times 2 is 2, and 2 times 3 is 6. Over here we have minus 4, and over here we will have 2. So we have 2 is greater than or equal to 2. And this inequality is true when n naught is equal to 2. For our conclusion, we will say, by definition, 3n log n minus 2n is big omega of n log n, since our function is greater than or equal to 1 times n log n, for all n is greater than or equal to 2. Prove that n to the power of 2 is not big omega of n to the power of 3. So we know that n to the power of 2 is not big omega of n to the power of 3, because if we write it in our inequality, we have n squared is greater than or equal to c times n to the power of 3. Intuitively, you know that this is not true, because this is basically saying that a quadratic function grows faster than our cubic function. And that is not the case. It is actually the other way around. We're going to use proof by contradiction. So suppose that n to the power of 2 is big omega of n to the power of 3. So if n squared is big omega of n to the power of 3, then this means, according to our formula, that there exists a positive constant c and a positive integer n naught, such that n to the power of 2 is greater than or equal to c times n to the power of 3, or n is greater than or equal to n naught. And what we're going to do is divide both sides with n to the power of 3. So we have n to the power of 2 divided by n to the power of 3, and that's greater than or equal to c times n to the power of 3 divided by n to the power of 3. But this is the same as multiplying by 1, so we can remove this here. Now, one thing to note is when we divide both sides by n to the power of 3, the sign stays the same. We don't flip the sign because n is positive, right? We're basically saying n is greater than or equal to n naught, and because n naught is a positive integer, then n will always be positive. But that's why when you divide by a positive variable, the sign stays the same. Also, n to the power of 2 divided by n to the power of 3 is the same as 1 over n. At this point, some of you may realize that this here is not true, right? Let's draw out the graph and see what this means. So if we draw out the graph, where the horizontal axis is n, c is a positive constant. So let's draw c. C is a positive constant, so it will be like this. And let's draw 1 over n. So 1 over n will look something like this. And notice that, let's say we pick, so let's say here is our n naught. So starting from n naught and going to the right, we can see that 1 over n, our function 1 over n, is always below our red function c. So in reality, this is true. But over here, it says the exact opposite, which means that this is our contradiction. We're going to write this is a contradiction since the limit as n approaches infinity of 1 over n is 0. Basically, we're just saying that this function is approaching 0, or it's approaching the horizontal axis as n approaches infinity. And the limit as n approaches infinity of c, right? So this is the line of c. So as n approaches infinity, it would just continue to be c. It's not going to change. Because of that, 1 over n is less than or equal to c, for n is greater than or equal to n naught. So this is the way to say it, and therefore, n squared is not omega of n to the power of 3. On the exam, sometimes they will ask you what is the difference between type big O and type big omega. Well, type big O is basically the slowest growing function among those listed. For example, let's say you're given multiple choice and you have to select which one is type big O. So here we have 2n squared is O(n to the power of 4. 2n squared is O(n to the power of 3. 2n squared is O of n to the power of 2. And 2n squared is not all of n. So because this is not big O, you can just simply ignore this one. And now you have 3 options left. According to our definition, type big O is the slowest growing function among those listed. We can see that n squared is the slowest one. So this one here would be the type big O. And you can even notice that this is n squared and this is n squared. So they're kind of like on the same order. What is type big omega? Well, a type big omega is the fastest growing function among those listed. And let's say you're also given 4 options and you have to select the one that is the type big omega. So let's see. We have 2n squared is not big omega of n to the power of 3. 2n squared is big omega of n to the power of 2. 2n squared is big omega of n. And 2n squared is big omega of the square root of n. So all of these statements are correct statements, they're true. But which one is type big omega? Well, first of all, you see that this is not big omega, so you can safely ignore this one. Now again, if you look at the definition, type big omega is the fastest growing function among those listed. So out of these options, the fastest one is obviously this one, right? So we're going to select this one. And you can also notice that here we have n squared, and this is also n squared, so they're of the same order. True or false? F of n is big O of f of n. So basically saying it's big O of itself. And the second one is f of n is big omega of f of n. It turns out that both of these statements are true. So if you use the inequality, you can see that f of n is smaller than or equal to 1 times f of n, right? So you pick c to be 1, and you can pick n naught to be 1 as well. And for this one, you also use the inequality, but this time f of n is greater than or equal to 1 times f of n. So c is equal to 1, and n naught is also equal to 1. So this is very important. F of n is both big O of itself and big omega of itself. And the last one is big theta. So big theta is actually always tight. it's always tight because it is like an equal to statement. So the formula for big theta is this. F of n is big theta of g of n if the two conditions are met. So the first condition is f of n is big O of g of n, and the second condition is f of n is big omega of g of n. And that's it for today. In the next video, I will show you how to use this formula to prove big theta.